This is part 3 of section 2.6. We've just talked about solving with complex numbers, and now we're ready for the fundamental theorem of algebra. And what it says is that every single polynomial, and the polynomial we have here is just written in general form, that where you have a degree larger than 1, so at least a square term, and that the first number is not 0, and you have complex coefficients. So theoretically, you can use this theorem even if you have imaginary numbers as coefficients. And it's going to have at least one complex 0. Now the thing to recognize is that complex numbers include integers and everything else. So it's going to have at least one solution. Okay? So the factorization theorem for polynomials looks like this, okay? If you have a polynomial and your degree is larger than 1, then it can be factored into n, not necessarily distinct, linear factors of the form p of x equal to a, which is just a constant, times x minus the first root, times x minus the second root, times, all the way down to x minus the last root, okay, where these are complex numbers. So this is just working backwards from the idea that we can factor everything and set each part equal to 0. Well, if we already know what gives us zeros, then we can work backwards and get it into factored form. Okay? Any polynomial of degree n has exactly n zeros, provided that a 0 of multiplicity k is counted k times. And that's just, multiplicity is just if you get an answer more than once. So if I get the number 5 3 times, then 5 has multiplicity 3. Okay? And when you're counting the number of roots, you're going to count 5 3 times. Okay. Now here, I'm just giving you a little bit extra here. This is not in your book. You do not have to use it. You do not have to memorize it if you do not want to. But as we go along with these problems, we are often going to have to multiply things that are in this form, where we have a complex number as a root, and here we have another complex number, okay? And often we're going to have to multiply these together. So x minus one complex solution and x minus the other complex solution. And if you do that, then you get this. I've just worked through all of it, but you can go directly to this answer, and that's going to be useful later. So you can use it every time if you wish. If you don't want to, you can go through this process every single time. It's up to you. Okay, but let's find a polynomial of degree 4. So I'm going to have, my largest exponent is going to be x to the 4th, with a leading coefficient of 3. So that means up here, that number is going to be 3. Okay, and I have a 4th degree polynomial, so I should expect 4 solutions, and I do have 4 solutions. Okay, so I'm going to write out everything here, including things that you would probably be doing in your head after you work a couple of these problems. So the polynomial I'm looking for has a leading coefficient of 3 times. Okay, now what this says is we do x minus each root. So I have x minus a negative 2 times x minus 1 times x minus 1 plus I times x minus 1 minus I. Okay, and they will definitely want you to simplify here for sure, usually here as well. And in fact, on this problem in the book, they want you to multiply all of this out. Okay, you want to pay attention to what specifically the problem is asking you for, because they may want you to leave it in factored form, basically like this, or they may want you to go ahead and multiply it all out. Now, I could have distributed here and gone on, but I do have something in this form right up here. So if I'm going to multiply these two together. Okay, your a value is here. Your b value is the coefficient of I, which is 1. So if I'm going to use this, my a value is 1, my b value is 1. I need a squared and b squared. And both of these are 1. Okay, so now if I'm multiplying these together and I'm just doing this part, that becomes x squared minus 2 times a times x, so 2 times 1 is 2x, plus a squared plus b squared, which is 2. Okay, so now let's go ahead and multiply these two together since they want us to multiply it all. And I'll get x squared plus 2x minus x, so that's plus x minus 2. Okay, now let's multiply these together by using FOIL, and I'm going to multiply 3 at the very end because that's the easiest thing to do. So, distribute the x squared, x to the 4th minus 2x cubed plus 2x squared. Distribute the x plus x cubed minus 2x squared plus 2x. And now distribute the negative 2 minus 2x squared plus 4x minus 4. Bracket. So combine like terms here. X to the 4th, and then I have negative 2 cubed plus x cubed, so that would be negative x cubed, and I've used these two. 2x squared minus 2x squared minus 2x squared. Two x plus 4x would be 6x, and then minus 4. And now finally distribute the 3 to get 3x to the 4th minus 3x cubed minus 6x squared plus 18x minus 12. And that's the answer they're looking for. Okay. Now for the conjugate pairs theorem. And we've sort of touched on this already. If you have one complex solution, you're going to have the corresponding one that has the opposite sign in the middle. A and A, the signs are the same, plus B minus B, okay? And if you think about the quadratic formula, and you'd get the I values, the imaginary part from the square root, and the square root has a plus or minus in front. So that's why you're getting both of these solutions. Start off with a couple of easy problems. Find the remaining zeros of the polynomial with real coefficients and with the specified degree and zeros. So I have degree 3, so I should expect 3 answers. I'm given 2, I'm asked to find the third. Okay, well here I have one complex solution, so the other one is going to be what we call its conjugate pair, and it's just going to be 2 plus I. Because if you have one complex solution, you have the other. And that does bring me up to 3 zeros, so I'm done. Okay. If I have a 6th degree polynomial, I need 6 solutions, and I'm given 3 of them, and they are all complex, so that means I just need to write down their conjugates. This is, just as a side note, 2i is the same thing as 0 plus 2i. So if you needed it, your a value would be 0 and your b value would be 2. But its conjugate pair would be negative 2i. The conjugate of 4 plus i would be 4 minus i. And then the conjugate of I minus 1. Now that's tricky because your real part is supposed to come first. So this should be rewritten as -1 plus I before you find its conjugate pair. And it's always the number in front of your I that changes. So the last solution here will be -1 minus I.